Good afternoon, pilot teachers, and good afternoon, students. Thank you. Sit down. Okay, we have completed our work on looking at air pressure, but there are a lot more activities and other extra information that we can also spend some time on before we move on to looking at the last topic in our book, which is on climate and vegetation. So we're going to spend the lesson today, mainly on looking at extra information together with what we have covered on air pressure. We're going to do an activity, and the activity that we're going to work on will be from this booklet here, which is titled Investigating Physical Geography. And the activity is going to be based on the movement of air that we have already covered. When we look at the horizontal movement of air, we are looking at winds. And at the same time, when air rises vertically, we are looking at air currents. But we're going to discuss a little bit extra on the movement of air further up in the troposphere. And an example of the movement of air further up in the troposphere that we have already looked at when we started off by dealing with the atmosphere, the different layers of the atmosphere, where the westerly winds or the jet streams. And our exercises today, or the activity that we will work on in our lesson today, will be based on the jet streams. I'll give you the activity later on. We'll quickly recap on what we have covered already on air pressure. We've looked at air will always move, or sorry, not air, but winds will always move from areas of high pressure to low pressure. On a non-rotating Earth, winds would look like what is shown on our monitor, blowing straight up, straight down from the high pressure areas to the low pressure areas. There are two distinctive low pressure regions that we have already studied about, the doldrums and the 60 degrees north and south. And we've also seen two distinctive high pressure regions, the 30 degrees horse latitude, north and south, and the 90 degrees North Pole and the South Pole. Movement of air horizontally, or winds, will generally blow from high pressure areas to low pressure areas. The diagram here represents a sample of if the Earth wasn't rotating, how the movement would actually look like. In reality, we know that the Earth rotates, and because of the rotation, the movement of air therefore deflects. And the deflection of the air to the right, or the deflection of the winds to the right or to the left, is referred to as the Coriolis effect. In the northern hemisphere, any free moving body, which is either air or water, would deflect to the right. In the southern hemisphere, free moving bodies of air or water would move to the left, or deflect to the left. Therefore, we ended up looking at the major planetary winds between the horse latitude and the equator. In the southern hemisphere, we have the southeast trade winds. In the northern hemisphere, we have the northeast trade winds. Moving away from the horse latitude to 60 degrees north and south, in the northern hemisphere, we have the southwesterlies, and in the southern hemisphere, we have the northwesterlies. And then from the polar regions towards the 60 degrees north and north and south, we have the polar easterly winds. The movement of air, again, is not straight up and straight down. Because of the rotation of the Earth, we can see the deflection in the different hemispheres. And the deflection, we have already learned, is referred to as the Coriolis force or Coriolis effect. We also looked at generally a diagram to help us understand on the path taken. I also mentioned to you that, remember, for you to be able to see the deflection to the right or left, you must stand with your back to the wind. So we know that the winds will blow from high pressure to the low pressure. In the northern hemisphere, if you stand with your back to the wind, you will always see that the deflection will be to the right. And in the southern hemisphere, if you stand with your back to the wind, then you will see that the deflection is always to the left. And this diagram here was to help you understand that deflection from high pressure to low pressure in the north and south, or northern hemisphere and southern hemisphere. Your homework was the completion of a cross-section, and that cross-section that you were supposed to have constructed should have summarized everything that we have already learned on pressure belts and prevailing winds, and the reasons for why there are high pressure areas and low pressure areas, and also how the winds operate or move on a large scale. The diagram is also found in your booklet, Introduction to Climate, and I think it's figure 21 that you were supposed to have made note of from your Introduction to Climate booklet. Figure 19, okay, so it's figure 19 from your booklet, Introduction to Climate. Okay, with that, we are now ready to look at some extra information, and the extra information that we are going to look at will be basically to do with air pressure and again movement of air. And today I'd like us to look at information basically on the spiraling effect of air into low pressure and also out of low pressure, and how they spiral or how they move in the different hemisphere into the low pressure areas and out of the high pressure areas. On the monitor, the information there or background readings to look at what I'd like us to cover in our lesson before we go to the activities. We've already learned about high pressure areas. Those are areas associated with sinking air. Low pressure areas are areas associated with rising air. Whenever a low pressure system is formed, air tends to flow into it. Okay, so whenever a low pressure system is formed, air will tend to flow into it. You remember the movement of air horizontally or winds? They will always blow from high to low. So if a low pressure system is formed, what will happen is air will tend to flow to that low pressure system to take the place of the air that has risen. Whenever a high pressure system develops, air tends to flow out of it. So the air sinks, it creates a high pressure area. At the same time, air flows away or out of the high pressure system to the low pressure system. However, from what we have learned already, the rotation of the earth has an important effect on all air movements. It causes the air to be deflected to the right in the northern hemisphere and causes the air to be deflected to the left in the southern hemisphere. That we have learned already. That is simply referring to the Coriolis effect. We'll move on. Thus, the air moving into lows and out of highs tend to spiral in and spiral out. So if we have to describe the spiral movement, it is simply a movement like this. That's spiraling. Okay, the spiral movement, air moving into the lows and out of the highs tend to spiral in and spiral out. We understand that so far? Okay, in the southern hemisphere, we're now looking at the different hemisphere. In the southern hemisphere, air will spiral into the low pressure area in a clockwise direction. So if we were in the southern hemisphere, if there is a low pressure, air will spiral into the low pressure in a clockwise direction. Do we know what clockwise is and counterclockwise or anti-clockwise is? Okay, clockwise, if we have a clock face, clockwise means going to the right. Okay, so if we are going, say for example, this is a clock face, this is 12, we have 6, we have 9, and 3. We are going from 12, 1, 2, 3, 4, 5, 6 in a clockwise direction. If we are going anti-clockwise, then it will be still the same, the clock face, but instead of going this direction, we will be going back, 12, 11, 10, 9, 8 in this motion. This is counter-clockwise or anti-clockwise. This is clockwise. Okay, in the southern hemisphere, where there is a low pressure, air will actually spiral into that low pressure in a clockwise direction in the southern hemisphere. So if we have low pressure, air will spiral in a clockwise direction into the low pressure. This is southern hemisphere. Then we also have the high pressure areas in the southern hemisphere. In the southern hemisphere, air will spiral out in an anti-clockwise direction in the southern hemisphere. So here, high pressure, air will actually spiral out in an anti-clockwise or counterclockwise direction. We'll give an explanation and some example of this very shortly. So we look at that again. We note that air will spiral into lows and spiral out of high pressure. In the southern hemisphere, where there is a low pressure, air will actually spiral into that low pressure in a clockwise direction. In the southern hemisphere, where there is the high pressure, air will spiral out of that high pressure in an anti-clockwise direction. We understand this? Okay, we move on. If we have to look at a diagram to show us the spiraling impact or effect of air into the low pressure and out of the high pressure in the southern hemisphere, our diagram would look like this. A low pressure area, the air is actually spiraling into the low in a clockwise direction. This is the southern hemisphere. Still in the southern hemisphere, where there is a high pressure in the middle, air will spiral out of the high pressure area in an anti-clockwise direction. Okay, perhaps I'll give you 1 minute or so to make note of that diagram to go with that information that we have just looked at. Okay, we've made note of the diagram. Okay, then we move on. This time, if we're looking at the northern hemisphere, the reverse is going to be true for the northern hemisphere. Okay, we move on now to the northern hemisphere. In the northern hemisphere, air will spiral into the low in an anti-clockwise and spiral out of the high in a clockwise. It's the other way around now in the northern hemisphere. Okay, we had the diagram here for the southern hemisphere. If we have the diagram for the northern hemisphere, we still have two clock phase. We should know the difference between clockwise and counterclockwise or anti-clockwise. Again, in the northern hemisphere, air will spiral into the low at an anti-clockwise. So this second diagram here will be low pressure, whereby air is actually spiraling into the low at an anti-clockwise direction in the northern hemisphere. Out of the high pressure, air will spiral in a clockwise direction in the northern hemisphere. So it is the opposite to the southern hemisphere. The southern hemisphere, air will spiral clockwise into the low pressure and spiral anti-clockwise out of the high pressure. In the northern hemisphere, air will spiral out of the high pressure clockwise and into the low pressure anti-clockwise. We have that information? Okay, now let's look at the diagram. The diagram to show in the northern hemisphere. Okay, we have the low pressure area here. This is now the northern hemisphere diagram. Air will actually spiral in a clockwise direction into the, is it clockwise or anti-clockwise? Into the low, sorry, it will be anti-clockwise. Yeah, the arrows going in that direction. So in the northern hemisphere, air will spiral into the low in an anti-clockwise or counterclockwise direction. And out of the high pressure, air will spiral in a clockwise direction out of the high pressure in the northern hemisphere. The spiraling effect then can be seen clearly, especially if you live in the temperate regions or further away from the equator, where the Coriolis force within the equator is actually at zero. It's not felt. If you move away from the equator, the Coriolis force is greater away from the equator. In the temperate regions, if you live in the northern hemisphere, you fill up a sink with water. You remove the plug from the sink, watch the movement of the water into the sink plug. It will always go in the northern hemisphere, it will always go in the anti-clockwise. The water will actually rotate anti-clockwise as it's going down the sink. If you were in the southern hemisphere, maybe in Australia, fill up the sink and then remove the sink plug. Watch the water, the way it will spiral into the sink hole. It will always go in a clockwise direction while it is going down the sink hole. In Papua New Guinea, we will try that. We will not be able to see much effect on the spiraling because, again, the Coriolis force is greatest away from the equator. At the equator, the force is at zero. As we move away from the equator, the force gets greater. Therefore, the deflections also is greatest away from the equator compared to at the equator. Later on, when we look at air movements, especially in the formation of cyclones, anticyclones, and etc., we would have also noted that where the equator is, cyclones will never develop or form where the equator is. But cyclones will form about 5 to 15 degrees latitude away from the equator. So if you live right along the equator, you are free from the effect of cyclones. But if you are about 5 to 15 degrees away from the equator, those are the areas where the path of the cyclones would actually take. Okay, looking at those air movements, again, very important in the movement of the air spiraling into the lows and spiraling out of the highs, and how they operate in the different hemisphere. Any queries or questions with regards to those two diagrams? Basically, this is showing us surface air movement or winds generally. Where there is a high pressure in the northern hemisphere, you will tend to find that the air will spiral. In the northern hemisphere, the air will spiral out of the high pressure in a clockwise direction. Into the low pressure area in the northern hemisphere, it will spiral into the low pressure anti-clockwise or counterclockwise. Okay, we have a question at the back there.
Why is there a difference in the movement of air in the both hemispheres?
Okay, we've already looked at, remember we've already looked at the winds, the major planetary prevailing winds. In the southern hemisphere, they come in especially between 0 to 30. From 30 to 0, they would blow in they come in from the southeast direction, therefore they are referred to as the southeast trade winds. The high pressure is at 30 degrees south. Winds will blow from high pressure to low pressure. So the direction is from the 30 degrees south to the equator. Whereas in the northern hemisphere, from the 30 degrees, it's coming down to the equator. So the winds are blowing from the north down to the equator, the northeast. Winds will blow from high to low. We have already seen the distinctive low pressure belts and the high pressure belts. So the different directions are according to the different pressure belts and the movements from high to low. Therefore, the directions are according to where the high is and where the low is. So if we're in the southern hemisphere, there are high pressure belts, host latitude 30 degrees south, and there is also the polar. The winds are blowing towards the low pressure, which is at 60 degrees and the equator, and they are coming from the south direction. Whereas in the northern hemisphere, again, we have the 30 degrees north, the 90 degrees north, and they're blowing down towards the low pressure. So they're coming from the north direction down. And that's what makes the difference in the direction of the winds, the highs and the lows. Answers your question. Okay. Any other questions? Okay, perhaps some more questions will be asked later on. Let's move on. And today we're going to look at the activity that I'd like us to actually work on. And the activity will be basically on, this time, moving away from surface wind. And we note also that the circulation of air on our planet is not only concentrated on surface winds. There are also air movements which are high up above in our troposphere. And those air masses that are moving high above, one of the examples is that of the jet streams, those westerly winds that we have already studied as one of the characteristics of the troposphere. The jet streams we have already learned are some of those air masses or winds that pilots, especially in the mid-latitude countries, would use to help them mainly getting from one point to the other a little bit more efficiently. Okay, now we look at the information from our booklet so that we are able to complete the activity which is given, activity 3A. Let's go through the readings, and then you will be required to discuss in threes the answer to the two questions that will be based on the readings. Okay, we're looking at well-scaled winds. We are going to read around the class, and we are going to get at least a student to read paragraph by paragraph so that we can complete that information before the activities. We'll start from the back, and we go around for our readings. Okay, Susan, you're going to start us off with the readings on page 86 and 87 of our booklet on the world-scaled winds. And together with the readings, it should be able to help us answer our two questions that you are going to work on. We check, we should at least have one book between 3 people because our discussions will be based, or our work will be done in group discussions. Are we ready to start with our readings? Yes? Okay, we'll start.
Yes. Figure 8.3 shows a section of the globe. Cold air sinks over the North Pole, causing high pressure with winds blowing out from the polar ice. Hot air rises over the equator, causing low pressure. This draws in air from both sides of the equator to replace the rising air.
Thank you, Susan. And I think with that also, that will maybe emphasize on the question that you asked, Ovio. Maybe it might help with the answering of that question. So, Ovio, we move on, paragraph 2.
The two spirals of cells of revolving air are called the polar cell and the Hadley cell. The latter is named after George Hadley, who first had the idea that these cells existed.
Okay, we're making reference to the movement of air, which is higher up into the troposphere, not the surface winds. Therefore, we are coming across with words like the Hadley cell and the polar cells. Okay, we move on, third paragraph.
Because the Earth is spinning around, winds in the northern half of the world are diverted to the right. Shows that figure 8.4 shows that the cells, rather than running north-south, are tilted so that the winds blow from northeast rather than from the due north.
Okay, again, that information we have covered because we have looked at the deflection. We should be able to understand the deflection of the winds in the different hemisphere. In the northern hemisphere to the right, and in the southern hemisphere, deflection to the left. Next reader, Christopher.
Hadley knew that in Britain the wind would blow most frequently from the west and southwest. For example, the winds in the Spitke. He thought that another cell would be found between the polar cell and the Hadley cell. This cell would rotate, powered by the cells on either side, like a cogwheel between two other spinning cogs, as well as as we shall see. He was not quite right.
Next reader.
What really lies between the polar cell and the Hadley cell? Part of the answer was found out during the Second World War when bombers flew at great height to be above the range of the simple radar of the time. What they found was often rather puzzling. For example, bombers from an airfield like the one in figure 8.5 were ordered to take off, fly west for 2 hours at an airspeed of 200 kilometers per hour, and drop their bombs. At the height they were flying, they were westerly winds blowing at the same speed.
Okay, so now we've come to that section. The next task that we are going to work on now is the discussion questions to answer figure, or not figure, but exercise 3. You have on a copy of figure 8.5. Figure 8.5 is also actually shown on the monitor. If you look at the diagram you have in your book and also on the monitor, the discovering of the winds that blew at about 200 kilometers per hour higher up in the troposphere was only during the Second World War, according to our information here. If the pilot, according to the information given, were asked to actually drop their bomb, but they have to actually fly about 200 kilometers before they drop their bomb, where do you think the bomb will actually fall? That's the first activity you are going to discuss. And you are going to put an X to mark where you think on that diagram the bomb will fall. The second question that you will work on: when the bombers, they flew back at an airspeed of 200 kilometers per hour for 2 hours, where do you think they would have landed? Again, you mark an X on the place that you think they would have landed. Okay, those are the 2 activities then for you to work on. You can discuss in 3s or 4s to complete those 2 activities. Can you go with those 2? You can mark on here, because when we do ask you to give the answers, you should be able to tell us why you have indicated that it's this point here. Yes, the 2 questions here. You see on the copy here, all you have to do is mark where do you think, if you were given the task, you're the pilot, you're given the task to go and drop the bomb at the target there. From the readings, we already found out that the plane will fly at 200 kilometers per hour for 2 hours, and they drop the bomb. where do you think the bomb will be dropped? That's number one. The second question, after they drop their bomb, they have to fly back another 2 hours at a speed of 200 kilometers. Where will they land? How much time? 9 minutes. Okay, we'll need to get some answers then from your discussions. You're working in groups, so we'll get a couple of groups to give us where they think the bomb will actually drop for the first answer and the reason for why you have selected that particular spot or that particular area. I will start from the front, and the students in front here will give their answer for question 1. Perhaps this is what we'll do. The students on this side here, in your groups, you are going to answer the first question, and the students on this side here, you'll give the answer for the second question. Okay, from the front. Show us where on the map or where on this particular diagram here, this bomb or that bomber would be able to drop their bomb and the reason for why you've selected that area. You ready? Not yet. Mason, your group ready with the answer to this question? Not yet. Dorothy, your group ready? Kiran? Anita, your group ready to give an answer for the first question? No. Christopher, you ready to give the answer for the first question? No. How about on this side? Ovio, your group ready with the answer for the first question? No. Gibes? Okay, thank you. Gibes and the group, they are going to give us the answer for the first question. Show us, where do you think the bomb is going to drop and why have you selected that area? Quickly, one of you to the front and indicate on the monitor. Because you'll have to show us exactly where on that diagram. Okay, while Gibes is actually coming to the front, we look at the question again. He's going to answer the question on if you were a flight or you're a pilot flying a plane to go and drop a bomb. You are flying at 200 kilometers per hour. The wind speed is at 200 kilometers per hour. The pilot takes off from the airfield. He flies for 2 hours and then drops his bomb. Where will the bomb drop? This group here is going to answer that question and also give us the reason for why they've selected that area. Okay, thank you, Gibes.
The bomb will fall between the two islands. If the reason is that if the bomb fell here, and when it drops here, the wind is gonna take it about 200 kilometers and eastward, so it will fall here.
Okay, according to that group,
Thank you.
their answer logic? Yeah, perhaps, yes. I'm not going to tell you that's the correct answer until we hear from maybe a couple more groups, okay? The group here has told us that the bomb will drop around here, about 200 kilometers. The reason being that the pilot comes over here, drops the bomb, the wind is blowing at a speed of 200 kilometers. The bomb, instead of dropping at the target, might drop around this region here. So that group has put down X here. Possible. Any other group would like to try where they think the bomb might drop? Gideon, thank you.
The bomb is going to fall on the target because the wind speed is equivalent to the plane's speed. So if the plane drops the bomb, the wind speed, the bomb against the wind speed is going to support the bomb and it's going to fall straight on the target.
Okay, according to his group, could be a logical explanation. Thank you. Any other groups with the explanation of where they think the bomb will drop? You have an explanation? Give us, sorry, Mason, do you have an explanation now? No? Christopher at the back, explanation? Okay, thank you. From the front here.
Our group will say that the bomb will fall right on the target because, as it says in the textbook here, the pilot is flying to the west 200 kilometers per hour at a speed of 200 kilometers per hour, and he's been flying for 2 hours. So that means the first hour from 400 kilometers he'll arrive here, and the second hour he's going to arrive here. And because the wind is against his direction, it will blow and help the bomb to go down straight right on the target.
Okay, so there are two groups of students now who say that it will drop right on the target. Okay, the alternative answer that could be given. Let's look at this. The plane takes off from the airfield, right? Flies at that altitude. The speed of the plane is 200 kilometers. The speed of the wind is 200 kilometers. Will the plane advance? Why? The force of the wind is equal to the speed of the wind. So the plane takes off to the top about that height. It flies at a speed of 200 kilometers per hour. It's flying west. At the same time, there are easterly winds that are blowing at a speed of 200 kilometers. There is an equilibrium force. Therefore, the pilot thinking he's advancing is stationary. So if he's taken off from this airfield here, thinking he's advancing, he's stationary, travels for 2 hours, it's shown, 2 hours already, then he decides to drop the bomb. Where does he drop the bomb? At the airfield, yeah. So that's what the answer is going to be. We consider the speed of the plane and we consider the speed of the wind. It's equal. So the answer will be at the airfield. Okay, now he's done the job. He's done his job. He's now turning back. And he's going to go flying another 2 hours for 200 kilometers. Sorry, he's going to fly another 2 hours at the speed of 200 kilometers per hour, right? So where do you think he's going to land now? Okay, he's going to land 800 kilometers away from the airfield. So when he's looking for the airstrip or the airfield here, he might not find it. Okay, remember we are looking at the westerly winds, the jet streams, and it was not until 1942, during the Second World War, that the pilots found that there was an air stream that is at that altitude, and that it was only recently that the pilots are now using it to help with navigation, or so not so much of navigation, but to get from one point to another more efficiently. But during that time, the pilots would not have known that there was this air mass moving at that speed. So they fly up to that particular altitude. They go for 2 hours at 200 kilometers per hour. The wind is coming to them at 200 kilometers per hour. There is an equilibrium force. After 2 hours, he drops the bomb. Bang, he hits the airfield. And then he turns around, goes another 2 hours, and he lands in the deep ocean. So our answer should be here, airfield, somewhere around here, for the first answer. And the second answer would be he should land around that area. Okay, that will also bring us to the end of our lesson. The rest of the readings that you're going to find in that booklet, you can actually do for your homework. Okay, class, if you could stand up now, please. To the pilot teachers, our keyword for lesson 121 is Coriolis. Good afternoon and thank you, students.